And after that, he obtained his PhD in the Queen Mary College from the University of London. And he was working, his thesis was on critical phenomena. After his PhD, he's been working in many places, but he worked, for example, doing dynamics on phase transitions in the Atomic Energy Commission in France. And before that, after that, he obtained the chair as statistical physics in the University Federico II in Naples, Italy. So he worked there for almost 30 years. His work, his scientific work, is focused on non-equilibrium statistical physics, and particularly in systems like with biological interest, but also statistical physics approach to biological evolution. So he is also, since 2017, he is the deputy director of Santa Marinella Research Institute. So thank you very much for being here with us, and welcome.
Thank you, and thank you for the invitation. And it's a pleasure to be here to visit Mexico and to discuss with people. I find that it is very interesting, exciting. I hope that you will like what I'm going to say. It's just general ideas about the point of view of exploiting information in a way that you can, for instance, extract work from a physical system, or you can turn your information into a game, or you can turn information into population growth. But these different phenomena have a common formalism, and so this is what I'm going to talk about. What is the language of acquired information, and in which way we can connect these different fields with common concepts. So this is more or less what I'm going to do. So I will give a general introduction, discuss some models. I will discuss what is the meaning of information reservoirs, and then do some conclusions. So the connection between physics and information was, say, at the first time established by Maxwell in popular work. In fact, it was a book which was supposed to give a first idea of what we call now thermodynamics for the general public. And there, you know, that he introduced the idea of a being that was able to look at a container which was divided in two parts with particles on one side and the other side, and this being would be able to distinguish between particles with higher energy than the average and lower energy than the average, and let the ones with higher energy than the average go, say, from right to left, and on the other hand block the attempt of particles with lower energy to move in the same direction. And if this was possible to do, then what you have at the end of the day is that you start with a container in which you have a gas with uniform temperature, and you end up with a container in which the left part of the container has a higher temperature than the right part of the container, and in this way you have created disequilibrium starting from equilibrium. But of course, in order to do that, this being needs to have some information about the state of the particles that are alive. So there is a connection between this information that the being is able to connect in some way that was not specified by Maxwell, and the process by which you get a reduction in the entropy of the system. And Lord Kelvin decided to call this being a demon. So this is why from there on you have a demon. The things that remain pretty much like that. There was some sort of debate in the 1880s about the role of this daemon, and basically they would say, well, it will never be possible to have such a precise measurement, but so therefore this is just sort of a philosophical question. And well, and after a while, so Szilard in 1929 tried to reconsider the same problem from a different point of view and see how you could reconcile this thought experiment with a demon which has these faculties with the second law of thermodynamics. And his idea was to reduce the same, to say essentially the same problem, that only you have a container that you can divide in two parts with a single molecule. Now, if you imagine that you have this container, you divide it in two parts with a movable wall, and you assume that you can put in and put out this movable wall without expending work. And there is only a single particle. Now, once you have divided the container in two parts, the daemon is able somehow to ascertain if the particle is on the right or on the left. Let's assume that, for instance, it finds that the particle is on the right, then it will be able to bind the movable wall to a device which, say, can lift a weight and let the wall expand the right part of the container reversibly until it goes to the end of the container. So you start from the particle is constrained on the right-hand side and half of the available volume, and it ends up having the whole volume at its disposal. And at that point, you are back to the original state. So you have a cycle, and in this cycle, you go from this original state again to the state A, but you have extracted a certain amount of work, which you can evaluate to be kT. So this is just the usual thermal energy of say, it's twice the thermal energy of a degree of freedom times log 2. So, and in this way, in principle, it seems that you are violating the second law of thermodynamics in the Kelvin statement that says that it is not possible to extract work from a single reservoir in a cyclic process. But in fact, there is something that has changed, and this is a crucial point. What is changed is the fact that the daemon has acquired the information about the state of the particle. And then at the end of the day, his memory is not exactly in the state that it was at the beginning. So the transformation is not exactly cyclic. So now I'm going to recast this process in which you have a certain amount of information. You translate this amount of information into some available work in different kinds of processes. So we consider different kinds of daemons that show that gleaning information yields some sort of power, because then you can use this information to perform a feedback and then get some.
What is gleaning?
Gleaning means taking. Is for instance, you go in a field that you find that has been cut, and you find that there are some grains. This is gleaning. So, gambling, population dynamics, and thermodynamics. Gambling, horse races. So this is a famous work which was done, in 47-48, Shannon introduced the concept of the entropy of a probability distribution. And in particular, he was interested in the communication and was trying to find the bounds for error-free communication, so the rate of information transmission. And Kelly in 56 had the idea of evaluating information rate in an original way. So he considers a case in which you have horse races, say repeating horse races, always with the same horses. And you imagine that you are able to bet on the different horses a certain amount of money. And the book, if the horse wins, the horse on which you have bet wins, then the bookies will pay OI times. So say that I is the label of the horse that you are betting on, and the bookies will pay OI times the bet. You assume that there is no track take, just for simplicity, and you can modify this, but no track take means that the sum of the inverse of these odds is equal to 1. It's a very generous rule. And then you ask, what is the best strategy? Now, the best strategy is you have a one-off. What is the best strategy? If you assume that the probability horse I wins is equal to PR. then if it is one-off, what you want to maximize is the return, the average value of the return. Now, what is the average value of the return? Is the probability that horse I wins times the odds, the bookie, and then times the amount of money that you bet on the horse. And you sum over all horses. You want to maximize this. But if you have, it is only one-off, then the best thing you can do is to maximize, so to put all your money on the term which is largest. That is the term for which the product of the probability times the odd is maximum. So that it's very trivial. You try to evaluate the probabilities of the horses, and you evaluate it so you know what the odds are. And then there is only one bet that wins. Now the situation is different if you have repeated races. If you have repeated races, whatever you gain in one race can be reinvested in the next race. Now, if you do it like in this way, then if for any reason the horse I does not win in the race that you're considering, and you have bet all your capital on this horse, you lose everything. So it doesn't make sense. It is better to divide your capital betting on different horses. How do you divide the capital? Now, the idea is that in this case you have that your capital is going to increase or decrease, but is multiplied by some random factor at each time. Multiplying by a random factor means that the log is increased by a random term at each time. So what you want to optimize, to maximize, is the sum of these random terms. So in this way, what you want to optimize, imagine that you start with a capital W0, and then you can evaluate what is your capital after n races. And in each race, say K is the label of the race, there is the horse IK wins. And if the horse IK wins, what you get is the odd of that horse, which are given by the bookie, times the fraction of the capital, DIK, that you have bet on that horse. So this is the quantity that you want. This is a random quantity, and you want to optimize the average of this thing. But you don't want really the average. You want to take the log and then optimize the average. Because in this case, what you have is a sum of independent terms, each with the same distribution. And then you have a very, very simple maximum problem, because you have to take a derivative with respect to BI with the constraint that the sum of BI, each BI is the fraction of capital you're betting on horse I. So the sum of the BI's gives 1, which is the total amount of money that you're going to bet. And it turns out that the best strategy is simply to bet proportionally to the fraction of the capital that you're going to bet on horse I is equal to the probability that horse I wins. And you see here, it does not depend on the odds. This is due to the fact that we are considering a fair bookie, so that has this, doesn't keep a track take. Now let's look at the situation. In a sense, if you have a perfect bookie, a very honest bookie that not only doesn't have a track take, but has an estimate of the probability for the horses to win, say that it is a PI, and then it will give an odd which is equal to the inverse of the probability. That is the honest strategy for a bookie. But now suppose that you have a friend who has looked at the training of the horses and will tell you, now look, the real probabilities for the horses are not PIs, are QIs. And assume that the friend knows what is really the thing. So in this case, what you have is that if you, instead of betting with the probability, with the BI equal to this probability, you bet with this fraction, you are going to have an average value of this log of the increasing factor of the capita will be given by this expression, in which you see you have QI, which is the probability of the horse winning, times the log of the odd times QI, which this is your bet distribution. And this will be given by this expression. And this expression is always positive. It's very easy to, always positive or zero. It is zero only if QI is equal to PI. That is, if in fact the bookie is right. So, so this quantity is a measure of the distance between this distribution QI and the a priori distribution PI, and is known as the Kullback-Leibler divergence, and is always positive. So in this way, you have a measure of what you can gain by the information that your friend has given to you, the fact that the real state of the horses is QI instead of
PI,
of the booby.
PI is the probability for horse I.
Yeah, PI is the probability for horse I. QI is the probability for horse, say, you assume there is an a priori probability, which is the one that the bookie knows. And so the bookie assigns the odd according to his information. If you have a better information than one of the friend, and if the friend is right, so we assume for the moment that the friend knows the truth, that distribution is QI.
Could you explain what a bookie is?
A bookie is the guy who collects the bets and then pays the wins.
Mm-hmm.
So it's a business, and they are usually not honest. So this is why it's mathematics. All right. Now, so we have seen that gambling, you can collect information and you can get money out of that. If the demon collects information and gets work out of that. And now we see a population. The population collects information on the environment and gets what? What does the population get? Gets children. It grows. All right. So consider a population of a certain number of individuals, and these individuals are in discrete generations, to simplify things. So you have the parents, and then they reproduce, and then we forget about the parents, you look only at the children. And they live in an environment, and the environment is random, in the sense that it can have a certain number of different states. These states are labeled by X. The individuals themselves can have different phenotypes. So the phenotypes come in different flavors. And we say some of the phenotypes are adapted to some environment and less adapted to other environments. To simplify the things, we assume that for each environment there is a perfect phenotype, and we label the environment and the phenotype by the same X. And again, to simplify the thing, we assume that it is like a horse race. The guys who get the good phenotype survive and reproduce, and the other guys don't survive, are lost. And now you see, so in general, what you have is that there is a fitness function that tells you the expected number of offspring with a given phenotype in a given environment. What you have is that in order to survive, the individuals in this population have advantage in doing bet hedging just in the same way that a bettor has an advantage of distributing its capital in the different horses. In this case, you have that each organism has an advantage in distributing its children with different phenotypes, so that if the environment changes in an unpredictable way, it is possible for some of the children to thrive, even if the other ones won't. So you evaluate what is the growth rate of the population size. That is, imagine that you're looking at t generations. You take this quantity that its growth rate is 1 over t times the average value of the log of the population size at the t generation divided by the initial population size. And then you find that this is given by this expression. Here you have, say, 1 over t is just, you have sum over the possible values of the environment times the sum over the whole history that you're looking at of the fitness function of the phenotype at a certain generation and the environment at that generation, and this is multiplied by the probability that the child has the phenotype file. So there is an analogy. So this is the bet that the parent makes for its children. This is the odd, and the odd depends on the combination of the phenotype and the environment, the state of the environment. And then you average over the distribution probability of the environment. This is essentially the same formula we've seen before. The only difference at this level is the fact that this fitness here, it does not really need to be only on-off. No, in the case of the horse races, we have that you only won if you go to the correct horse. But you know that even in betting, you can have, say, what is called triple. No, you say, well, the horse will be among the first 3 ones. So in this case, you have an analogy like that. The mathematics is slightly different, but say we can just for the sake of the argument, we take again a horse race analogy in the case, assuming that you have to find exactly the correct phenotype for your environment in order to survive, and then you are rewarded by a certain number of average number of children, k of x. But it can be relaxed, and then you just plug it in the formula that I showed you before, and you can evaluate what is the growth rate of the population. And it's given by these 3 terms that are, so there is a maximal growth rate that you can have in principle that is given just by the average of the log of this fitness k here. Then there is a negative term which is equal to the negative of the entropy, Shannon entropy of the distribution, which is a measure of the dispersion of the distribution. Of course, if you had only one kind of environment, you would always win. And so just because the environment is random, then you have to reduce your expectation. You cannot do better than this. And then you have another term, and this term is, you see, is a px, the sum of x, px log of px divided by dx. It looks like the Kurbach-like divergence that we have seen before, in which you have the probability of the environment divided by the bet, the distribution of the phenotypes among the children. So this term here is, again, because of this minus sign, is always negative, but it can be 0 if b of x is equal to p of x. That is, if you use the Kelly strategy. So you have that the Kelly strategy cancels this term, and you get the maximum. So for the optimal strategy, you get the maximum of the optimal growth rate, which is given by this ideal growth rate minus the entropy of the environment. In the case of a fair gambling, like in the case of the honest bookie that we have seen before, that means that this k of x is equal to the inverse of the probability of the environment, and then the optimal growth rate is equal to 0. And this is connects with what we have said before for gambling. Now, acquired information. Where is the friend in this case? Well, the friend is the fact that organisms have a way of sensing the environment, that they are not completely naive about what is going to happen. So, usually what the organisms do is that they are able to measure some property that is related to the state of the environment, what I call a cue. So there is some random variable that I call a Q that is a partially informative about the environment. If Q has some value Y, then it tells you that there is a probability pi of the P of X given Y that the environment is in state X. So in general, what you write it as a joint probability having the environment in state X, the Q in state Y, and this, let's write it in this way by using of the Bayes theorem, is the probability a priori of having environment X, and then there is a conditional probability of the Q given the environment. This is what is really in. But of course, the organisms are not interested in the probability of the Q given the environment. Are interested in the probability of the environment given the Q. So consider and then once they have the probability of the environment given the Q, they have to assign the phenotype. So at the end of the day, what you want to evaluate is something that is the strategy of the organism will be to measure the Q, they get the value of the Q, guess the environment, and then assign a probability to the phenotype. And so this is what you want to have, is a conditional probability of assigning the phenotype phi once you have a Q bar. Is that clear? Now, given this strategy, so this embeds the strategy of the organism. You evaluate again the asymptotic growth rate. The asymptotic growth rate is given in terms of the joint distribution of the environment and the Q times the log of sum over all possible phenotypes, conditional probability given the Q of choosing that phenotype phi, times the fitness of the phenotype phi in the given environment. So remember that the Q does not specify uniquely the environment. It only gives you a probability distribution. So you optimize this strategy by saying that you want that the probability of the phenotype given the Q is equal to the probability of the environment given the Q. This is just a Kelly strategy. And then you use the Bayes theorem to express this in terms of that. And what you get is, again, this expression. In this expression you have, well, first term is, we already know, is the ideal growth rate, which is completely unattainable. Now you have a second term, and the second term you can write in this interesting way. There is one contribution which is just minus the entropy of the environment by itself, which is the same that we had before. But then there is an extra term here. This extra term is a measure of the correlation between the environment and the Q. It's called the mutual information between the two, and is always positive. That means that these two terms together are larger than they were in the absence of sensing the environment. And then you have this other term, which is always negative or vanishing. This term is interesting again. It's the sum over the joint probability distribution of the ratio of the conditional probability of the environment given the Q and the conditional probability of the phenotype given the Q. So if this pi is equal to this P, this goes to 0. And that is the maximum you can get. So this is the optimal result that you can have. And so the only thing is that I want to give an explicit expression to this mutual information. This mutual information again looks like a Kullback-Leibler divergence. So it is the sum over the joint probability distribution of the log of the joint probability distribution divided by the probability of the marginals. What you get for the distribution of x summing over all possible y's, and the probability of y summing over all possible x. And therefore this quantity only vanishes if x and y are independent random variables. So this is a positive quantity whenever there is some dependence between these random variables. Now, starting from what we have seen, the difference in the growth rate without the Qs and with the Qs is given by this mutual information. And you can generalize in the case in which you say, just consider what happens if you have the difference between the optimal conditional strategy and the unconditional strategy we've seen before. And this again, you find that there is a correction term, and this correction term is, is always negative, and the maximum value you can get is the mutual information. So we can identify the fitness value of Qs by this mutual information. Now, this is not complete, is not just abstract. Now I'm going back to a physical system, and we see how you can perform a Maxwell-Demon experiment with feedback by using Qs. So this is an experiment that was done in Japan in 2010. And essentially, the idea is that you imagine that you have a Brownian particle that can jump on a staircase, just like that. Because of thermal fluctuation, from time to time, the Brownian particle goes up one step or two steps. But say, on average, it will go down because it tends to dissipate energy. But now the idea is that imagine that you have a demon that is looking at the particle, and whenever it goes up, so it has a barrier. If the particle goes up, it puts the barrier down, and then waits. So one day or another, the particle will go up, and then the demon will move the wall up. And so if you wait long enough, the particle will move up. This is done with, so you have two colloidal particles which are bound together, and they are connected to a plane by, polymer, and which so that this system can turn around essentially without too much work. And what you have is that there is an electric field. You can have an electric field which can be put in, say, in one direction or in the other direction along the diagonal of the square, so that the potential felt by this system is a periodic potential that looks like in this way. But in the actual position of the maxima and the minima of this potential depends on whether the field is applied along this diagonal or that diagonal. So you have one state of the external system corresponds to the blue potential, and the other state corresponds to the red potential. Now, what you have in general is a situation like that. In principle, the particle will like to stay at the bottom of the potential, whatever that is, and then fluctuate around there. So here we are in the blue potential. But then from time to time, it will go beyond some point and reach one of these gray areas. So, and if it reaches the gray area on the right, you change fast your electric field, so that this maximum turns into a minimum, and you trap the particle there. So in this way, by performing this measurement, you are using the measurement in order to extract the energy of the particle from this level of the potential to this level of potential. And this is a way of extracting this amount of work, which is of the order of kT. So this is these are a number of trajectories that you can have as a function. So the thing that you are that you change here is the rate by which you are measuring the position of the particle. If you measure if you wait too long to measure the position of the particle in order to exercise the feedback, then of course the particle has the time to go down. But if you measure in sufficiently fast, then you see that you can go up. But in fact, it is very fluctuating here. You see that there are several fluctuations. And this is the amount of work that you can extract as a function of this, say, time between measurements. And there is this region here in which you can extract work. And otherwise, for longer times, you go down in energy and you lose basically. Now, what is the analogy between gambling and work extraction? This is really the analogy that I had just shown before. Just say, to simplify the thing, instead of having a staircase, we consider just a particle which can be only in two states. And let's call, say, state 0 the one which has lower energy, state 1 the one which is upper energy. But you can exchange the labels. And if you exchange the labels when the particle is on the up state, then you are going to gain this delta E of energy. So imagine that now you can perform a partial measurement which tells you with some probability which state the particle is in. So the measurement acts like the frame and allows you to extract work. And you can say, in this case, the strategy is quite easy. As long as the measurement has any sense, it means that it is correct more than half of the times. And then the best strategy you can use is the fact that if the measurement tells you that the particle is up, you switch state. If the particle is down, you let things stay as they are. And you can evaluate how much work you can extract. This is again, you use, say, the system energy is defined in this way. The energy of state X is equal to X times delta E. The energy E1 of X given the measurement is given by this expression, which tells you that if Y is equal to X, if Y is equal to 1 and X is equal to 0 is equal to delta E, and so if you say if Y is wrong, you have delta E. If Y is right, you have 0. And the extracted work is given by the state of the particle. And so this is what you get out of the manipulation. And so the energy of the particle minus, say, this effect of the error of the Q. And so, well, it has this expression. You evaluate the average. And then you define your conditional strategy in this way. Say, considering the probability of switching or not switching. And so at the end of the day, what you get again, that the average value of the average work that you can extract per cycle in this case, given by KT. And here you find, again, a Kurbach-Leibler divergence of your strategy divided by the probability that the system is in state X. And therefore, you have that the average, so this is the same expression that we had for the increase of the population. The average extractive work is analogous to the growth rate of the population, and this conditional strategy here is analog to this conditional strategy that we had in the case of population, that decide how you distributed your bets according to whatever information you have about the horses or the environment. So we have this table of analogies. So you have a gambler. So in the case of gambling, you have a gambler corresponds to the demon. In case of thermodynamics, it doesn't really have an analog with the population. In the case of gambling, you have a bets option on the bets. So this corresponds to the state, thermodynamical state. In the case of population, becomes a phenotype. The log capital growth is what you want to optimize. In the thermodynamics would be the extracted work. And the case of population is the log of population size. The side information given by the friend in thermodynamics correspond to the measurement, and the population corresponded to the cues that acquire information. And you can also generalize this to the case of non-equilibrium, which would correspond to a memory, so the fact that the races are not independent, or the fact that you have inherited information in the case of population. The population remembers what the environment used to be, and the environment itself is no more independent, but is sort of macro. There is a difference between the case of population and the other cases. And the reason is that the population, of course, is made of different individuals, and different individuals can have different sensing. So they have some sort of shared information. You can prove that in this case, the fact of having shared information gives an advantage to the population that you can evaluate. For the people who know the statistical mechanics of disorder system, the analogy is the one between the annealed averages and the quench averages. The annealed averages of a free energy in disorder system are always larger than the quench averages, and this is the advantage that the having, say, sensing in different individuals, that they can collect more information about the environment than just as imagine a centralized information, which may have some implications also for social systems. To think about it. Yeah, I think that, so this is just to summarize, usually we consider the case of Carnot engine. The Carnot engine is a system by which we extract energy as heat from heat reservoir. We provide some energy to a heat reservoir at a lower temperature, and of course in this process you are taking some entropy from the higher the heat reservoir with higher temperature, and we have to give some entropy to the reservoir at a lower temperature, and we extract some work. And when we extract some work, we are not providing entropy to the mechanical system. The mechanical system does not have entropy by itself. So what the best you can do is when the entropy you give to this reservoir exactly matches the entropy that you have taken from this reservoir. And of course, you can also, in this case, you can also do the reverse process, and you have a Carnot refrigerator, and you have this Carnot criterion of efficiency. Now, what I want to suggest is to consider also the possibility of having information reservoirs. So work reservoir is a system that can exchange energy without exchanging entropy. So it is analogous to have a thermodynamical system at infinite temperature, because the change in entropy is the change in energy divided by T. An information reservoir is a system that can exchange entropy without exchanging energy. You can imagine it's like a tape, and you imagine that you can flip the tape without spending energy, because the states of the tape, if it records a 0 or records a 1, have the same energy itself, and you can devise a way that does it without actually dissipating energy. So what you have is that in this case, in the balance, you have an extra player in the balance of the entropy that is an information reservoir. And you can imagine also information-fueled engines. So imagine that we have seen the Szilard daemon. The Szilard daemon converts the knowledge of the position of the particle in one side of the container into work that can be extracted. So a KT log 2 work. Now imagine that you have a tape of Szilard engines, all in the state 1. You can churn it with the daemon, you end up with a tape in which you have zeros and ones at the end of the manipulation, but you have extract on average KT log 2 per case. So you can use this work that you have extracted to push the locomotive. So in this context, what is the Maxwell daemon doing? Well, the Maxwell daemon is collecting energy and entropy from, say, low temperature, and then releases some energy and a certain amount of entropy to a higher temperature, because it is refrigerating in some sense. But in this case, you have that there is a mismatch of the entropy. Where is the extra entropy going? The extra entropy is going into its memory that acts like an information reservoir. So you have that the best you can do is when the sum of these two entropies that are released is equal to the entropy that has been introduced. What is the Szilard daemon doing? The Szilard daemon starts with, so you have only one heat reservoir, you take a certain amount of energy and therefore also a certain amount of entropy. Now you take some entropy out and you are left with a certain amount of entropy, and you take some energy out, you are left with a certain amount of entropy. This entropy goes into an information reservoir. Again, is the daemon's memory. At the beginning it was clean like newborn memory, and now it has some memories, probably not very exciting, but it does. And this has been done, in fact, in a single electron Szilard engine. It's a group of Pekka Pekkola in Helsinki. So what you have is, you see, this is essentially well, an electrode which is divided in two parts. One of them, this one is superconductor. They have many electrons, but the thing is engineered in such a way that can be in excess of at most one electron. And you can control with the gate here, and you have this single electron transistor that is able to evaluate the excess charge. And so you have the system is maintained at this temperature. One island is made of copper and the other one of aluminum. The charge difference is monitored. It's only one electron at most. So you have that the gate of this is the potential of the gate, and you have the charge is given in this way, in such a way that the gate is chosen in such a way that this excess charge is equal to 1/2. So you have equal probability for the electron to be on one side or the other. Now, via this single electron transistor, you detect which ion has excess charge. And once you know that it is in the one of the side, you change rapidly the gate, and then you move it slowly back to the initial value. This is exactly like in the Szilard process. You manipulate the system via this gate potential. And this is what you get. So this is you see that you have a measurement, and then this is the Ng, which is essentially a function of the gate voltage. You see that there is a measurement tells you that the excess is, say, negative, and so you move it rapidly to some low value, and then you move it slowly back to zero, to the say reference state. This is measured in terms. You see, the reference state is the one in which Ng is equal to 1/2. So this is the reference state again. And this is the measurement of the single electron transistor. So at the beginning, it just remains on that side, and then it starts jumping up and down like that. And then eventually, when you are in this region here, you see that the probabilities of being on one side and the other more or less equilibrate. Okay, so you can evaluate what is the change of the energy. So this is with the correct feedback, and this is with the wrong feedback. this is the value of the energy as a function of the gate voltage when there is occupation 1, this is when it is occupation 0, and this is the kind of, say, if you project that trajectory onto the energy ng space, this is what you do. Now, the interesting thing is that you ask what is the probability distribution of the work that you can get out in this system. This is, so again, the histogram of the work in units of KT. I don't remember with these different states. I think they depend on different manipulation protocols. But what you see interesting here, you see this corresponds to the value of the wrong manipulation. This is of the right manipulations, and you have a certain average value. But what is interesting is that if you shift now this histogram by the mutual information between the single electron transistor and the system that you're able to measure, you see that this histogram is peaked around 0, and this corresponds to this optimal regime that we have seen, in which a maximum effective work you can get is increased by the amount of mutual information between the measuring apparatus and the system. So to summarize, say that there is a deep analogy between the growth of capital, the growth of the population, and work extraction. And this, in fact, this information can be converted, the information about the system can be converted into dollars, into offspring, or in work. And this leads to a very interesting number of relations that I'm not going to discuss today that are related to the fluctuation theorems of stochastic thermodynamics. And in fact, in single particle experiment, you're able to touch the value of information in physical systems, and there are also experiments on biological systems, because of course, in one way of looking at biological systems as physical systems, they are essentially information driven. The main point of a life form is to provide information, its own information, to the next generation. So the information is really at the heart of the working of the biological system. So I thank you for this.